Assalamualaikum, my name is Nabil Asyraf bin Abdul Rahim. My mention number is DE18096 and I'll talk about introduction. In a modern day life, and industrial machines such as elevators, precision machinery, and sewing machines are considered an essential appliance. Most people in the world need this electrical appliance and use it every day. It needs an electrical supply to work properly. Other than that, one of the important components of this appliance is the motor. A motor driver converts electrical energy into mechanical energy. A motor can be alternate current AC motor or direct current DC motor. The focus of the project is to learn how to control the speed of a DC motor drive for a small-scale application. There are four main types of DC motor, which are permanent magnet DC motor, series DC motor, shunt DC motor, and compound DC motor. The system will contain one DC motor, speed controller, and a microcontroller algorithm. An analysis from the simulation will be obtained from the project. Adjustable speed drive or variable speed drive describes the system of equipment used to control the speed of machinery, where speeds may be selected from several different preset range. Usually the drive is said to be adjustable speed. These types of speed drive may be purely mechanical, electromechanical, hydraulic, or electronic system. In this project, we have to simulate base variable speed DC drive for a small-scale model application. The account of the availability of speed controllers is a wide variety, conveniently and in many ways. Speed regulation is very critical in most applications. For example, the DC motor in the radio-controlled vehicle, if only constant power is applied to the engine, the desired speed could not be sustained.
Hello, my name is Faradilah Afiqah binti Hasan, metric number DE180186, and I will explain to you about the problem, issue, and analysis of past research related to the variable speed of DC motor drive application. The issue is, in real world, the optimal speed of motor application can only be used at half of its maximum speed. To switch the DC motor, variable resistor is used to calculate the variable resistance in series with the motor. Typically, this approach has some drawbacks such as resistor releasing wasted energy as heat and not working on some computers such as microcontroller or other digital equipment for automatic DC motor speed control. Next is the buck converter, which are designed for supply all load varying conditions and set the voltage variations. Any change in the input voltage are designed to reduce the output voltage of the buck power converter as well as the motor input current. The obtained result in this paper show that regardless of the variation in speed and torque, the voltage cannot be varied. Next is speed controller. For control DC motor speed, some controllers such as fuzzy logic controller, neutral network controller, PIPD, and PID controller may be used. The controller operates by detecting the error in the system and analyze the reference signal and feedback signal to create the actuating signal. The PID controller turning is start by insert multiple set of parameter value generated by the controller. Next, it determines the set of gain KP, KI, KD by evaluating the step response of the system, and the response such as time rise, overshoot, steady state are obtained eventually. Last but not least, the step of this process will be repeated until the best value is made.
Methodology. My name is Farhana binti Husin. My metric number is DE180102. First one is system design. The aim of this project is to develop the variant speed DC motor drive for small-scale motor application by varying the speed of DC motor to control the voltage of the system. First one, we have a reference speed, a controller, speed controller, a converter, DC motor, and load. I'm gonna explain at a flow chart. From here we can see the signal from a specific speed reference. We go to the PID controller for training the signal, and we go to the algorithm where is the signal we calculate with automatic modeling, and we get the output speed is continuous, and we go to the buck converter for converting the signal, and one is go to the motor, and if the signal is not the same as the speed reference, then you're gonna go back to the PID controller and repeat. We have plot diagram. Here is the reference. Go to the summing junction. We have a PID controller. As I said before, we go algorithm. Here is 0.23, where is our troubleshoot error, and buck converter is 2. And go back to feedback is our gain to convert the signal from rad per second to get the RPM unit. So speed sensor is for measuring the speed. This is our second of closed loop variant speed of DC motor drive with PID controller. We have a 7 part of components that we use in MATLAB software. Here is the symbols. This DC voltage we use for a supply. Pulse generator is component that will produce pulse. Here is a PID controller. P is stand for proportional, I stand for integral, and D is derivative. We use to complete the closed loop system. This is buck converter we use for reduce the voltage from input voltage. It works at vary the pulse input from 0% to 100%. So the last one is the DC motor. Convert electrical energy to mechanical energy. First working principle is adjusting the armature voltage of DC motor. The type of motor that the simulation use is the liberated side motor that can have capability to run 1750 RPM. which armature and field voltage is supplied with 240 volts and 300 volts. It consists input mechanical select. Torque is 20.3 that we have calculated. So the second key principle is adjusting the supply voltage from the buck converter. Okay, we set up the buck converter with 240 volts and 40 kilohertz. The duty cycle is we override. We adjust at 50%. The output voltage of the buck converter will be go to 124. The algorithm is we calculate the duty cycle. Here is the formula of duty cycle for our system. So last one is our troubleshoot. How we troubleshoot our system is we use E2 formula of power and we can get duty cycle formula. From that, we assume with three type of speed. It's 165, 168, and 1269. From all the calculation, we get the troubleshoot percentage is 0.23 for differences of them. Formula from duty cycle before, we get and we plus with 0.23 for make sure the output speed of the motor to supply to the load continuous with reference speed.
Hi, my name is Hafiz bin Rosle, DE180159. So now I will explain about the working principle of the closed loop variable speed of DC motor drive and its example. So this is our simulation that conducted by using MATLAB simulation software. So we have a few blocks here. The first one is a block for desired speed, which is the value of motor speed that we want to set. And this is a PID block, and we have the algorithm block, which is used to convert to calculate the value of duty cycle. And this is a combination of block that used to convert the duty cycle value into the pulse. And here we have a DC buck converter, which is used to reduce the voltage output. And we have here a DC machine, which is have a constant load at 20.36 Nm, and the motor running at 1750 RPM at full speed, and the armature voltage is 240 volts, which is can be varied by using buck converter. And we have the field voltage here, which is fixed at 300 volts, and the output of the motor is the motor speed in RPM, and the armature voltage, field voltage, and torque. Okay, so this is the feedback for the motor. Okay, firstly I will run the simulation without the PID first, and the desired speed is 350 RPM. Okay, we will try to look the motor speed without the PID first. Okay, so after run the simulation for 0.5 seconds, so this is our desired speed in blue, and the red one is the obtained speed. So our desired speed is 350 RPM, but the obtained speed is only at 296 RPM, which has a huge difference from the desired speed and obtained speed. So to reduce this speed difference, we need to add the PID block diagram here, and by changing the value of the P, I, and D. Now I will try to run the simulation by changing the value of P. Currently the value of P is 1, and I will try to change the value of P into 10, and we will see the difference after we change the value of the P proportional into 10. Okay, I will try to run the simulation first. Okay, this is our result after we change the value of P to 10. So the obtained speed is 594 RPM, and our desired speed is 350 RPM, which is significantly increasing from the proportional value 1 after we change the proportional value to 10. Okay, so to increase the value into closer to 350 RPM, we need to increase the value of P. Okay, after try to change the value of P, the best value of P is 70. Okay, so look, the value of the obtained speed is now closer to our desired speed, which is 342 RPM. Okay, so to adjust the value to make it closer to our desired speed, we just need to add the I, which is integration here. Okay, so the value of I is 35. Okay, this is the result after we add the value I, 35, I integration. So the obtained speed is now close to 350 RPM, which is 349 RPM for obtained speed, and our desired speed is 350 RPM. But the problem is the overshoot here and the other term here. So to reduce the overshoot and other term here, we need to add the derivative value. Okay, the value of derivative is now set at 0.5. So this is a final graph after we add the P, I and D, which is the value of P is 70, I is 35 and D is 0.5. So there is no overshoot here and the addendum can be significantly decreases, and the motor is running at 649.5 rpm, which is very close to 650 rpm. So we can conclude that by adding the PID function at the our system, the other dam overshoot and the speed can be obtained as our desired speed. Okay, thank you.
Hello, Assalamualaikum. My name is Nur Azrini binti Azhar. My metric number is DE180152. Okay, so I'll proceed for the next part of demonstration. Okay, for my desired speed, for the second desired speed is 1200 RPM. Okay, so this is our basic circuit on the MATLAB. Okay, first of all, I would like to run without any PID controller. Okay, so run and then okay, the obtain speed like almost steady state right now. Okay, so as you can see for the scope, alright, so this is our result. So which is mean the obtained speed is 650 only, while my desired speed is 1300. Okay, so for the next part, I would like to apply the P first, the P mechanism, P gain. So I will run first and then okay, so the result obtained, the obtained speed is 1291, which is almost to 1300 rpm. Okay, so the overshoot start rising up. Okay, so for the next part, I would like to apply the I integral gains. Okay, so this is PI controller, because the P and I only we apply into this circuit. Okay, so okay, so the result obtained. Okay, the obtained speed for the steady state of the obtained speed, okay, 1300, exactly the same as desired speed. Okay, but as you can see here, have a little overshoot here and the settling time is not nice. So we proceed to D, derivative gained. So we run first. Okay, so the obtained and desired speed. Okay, so nice. The pattern, okay, there is no overshoot there. Okay, so the steady state is so 1300. Okay, exactly like this desired speed. Okay, so as you can see, okay, the duty cycle 0.79, which is almost to 0.8. Okay, for the next part, I would like to compare the value of 650 rpm and 1300 rpm DC motor drive speed. Okay, so for the gain value, as you may see, for the 650 rpm, 70, 35 and 0.5 is needed. And while for the 1300 rpm, the KP 138, while the KI 25 and KD is the same, goes to 650 rpm, which is 0.5. Okay, so without PID, as you may see, the difference is so big because of the desired speed applied. Okay, so with P 70 and 138, the 650 rpm, the obtained speed is 641.8, so it is almost the same, while the 1300 get 1291, while with the PI controller 649.3 and the 1300 1300 rpm is exactly the same, while for the PID controller, the final result of the 650 rpm desired speed, the obtained speed is 649.6, which is 0.4 difference, but it is actually quite the same, and the 1300 rpm is the same. So the controller response is, this is the conclusion of the controller response. Okay, for the rise time, overshoot, settling time, and steady state error for each gain, which is proportional, integral, and derivative. That's all from me. Thank you.